In this first video, we're going to be learning about how to multiply and divide radicals. So if you remember from last time, the index is a number that's kind of up there in the radical, and then inside the radical is called our radicand. So if we are trying to combine two expressions, two products, which is multiplication, we can combine them if they have the same index. So if the nth root of a and the nth root of b are real numbers, then the nth root of a times the nth root of b is the nth root of a times b. So we can combine on the inside. So can multiply if they're the same index. So let's see a few examples. In this first example, we have the square root of 2 times the cube root of 6. Remember, if there's nothing written up here, there's actually a little 2. So in this case, we have an index of 2 and an index of 3. So no, we can't, because there's different indices. There's just the plural for index. Let's take a look at the second one. We have the cube root of -4 times the cube root of 2. In this case, we have the same index, so we can multiply on the inside. So we can make this the cube root of -4 times 2, which is the cube root of -8, which is just -2. So now we're going to review first. So remember, you always have to put your solutions in simplest form. So you can reduce radicals by looking for multiple factors in the radicand. So we can do this with the factor tree, or we can do this by looking for cube roots or perfect squares or perfect cubes. So if we have cubes, we have to remember our perfect cubes. And these numbers are like 1 cubed or 2 cubed, which is 8, or 3 cubed, which is 27, and so forth. So if we have the cube root of 24, we can think, are there any cubes that go into it? And I know 8 goes into 24, so I can rewrite this as the cube root of 8 times 3. Now I have the multiplication problem on the inside, and I can actually do the reverse. I can break it into two separate multiplication problems. So the cube root of 8 times the cube root of 3. The cube root of 8 is 2, so I can write this as 2, the cube root of 3, which is the most simplified we can get. I could have also used my factor tree and done, oh, well, this is 8 times 3, and this is 2 times 4, which is 2 times 2, and I looked for a pair of 3 to take outside. In this next example, I have the cube root of 54 times x to the 5th, and I know 27 is a perfect cube that goes into this, so I can rewrite this as 27 times 2. And now I'm going to write x to the 5th so that there's something that can be taken out easily. So I'm going to write this as x cubed because there's a 3 here, so they match. So x cubed times x squared. Now I'm going to break this down into separate multiplication problems. You can kind of skip this step once you feel comfortable and just do this by looking at each part individually. So this is 3. Now the cube root of x cubed, these cancel out, which is just x. And now we have 2 terms left over that can't be simplified, so I'll combine them again. And here is our final answer. So now we're kind of going to be doing the reverse at first. We have 2 multiplication problems, and we're going to combine them. So when I combine these, I can just multiply everything on the inside. So I can take 72 times 10, which is 720. I can take x cubed times x. Remember, if there's no exponent, it's really a 1. So x cubed times x to the 1st. And then y squared times the y cubed. When I combine this, remember, if I multiply things with the same base, I add the exponents. So I say x to the 4th, y to the 5th. Now it's time for me to simplify. So I'm going to simplify as much as possible. Notice I have an index of 2, so I'm looking for a square. So my perfect squares that I kind of want to look for, I can either look for them or I can do a factor tree. My perfect squares are numbers like 2 squared, 3 squared, 4 squared, 5 squared. So it's always helpful to kind of have these off to the side if you need them. But once you do enough problems, you start to recognize them. So square root of 720. I know that 144 is a perfect square, and it goes into 720. And I know x squared times x squared is x to the 4th, and y squared times y squared times y is x to the 5th. Now I'm going to simplify as much as possible. So the square root of 144 is 12. The square root of x squared is just, they cancel out, it's just x. The square root of x squared is x. The square root of y squared is y. Same this. And then on the inside, we are left with the square root of 5y. And now finally, I'm going to combine. So this becomes 12 x squared, y squared, the square root of 5y. Let's try another. So I'm going to start off by multiplying everything. This time I can kind of just multiply as I go. So 45 times 35 is 1,575. X to the 5th times x, remember it's really like x to the 1st. I add my exponents, 5 plus 1 is 6. And y cubed times y to the 4th, I add my exponents, 3 plus 4 is 7. Now I'm going to simplify. This one's a little bit tricky. I know 15 squared is 225, and that goes in, so I'm going to do that one. Or remember, you can always use your factor trees, so go back to the other video if you want to remember how to do that. Now I have x squared, x squared, x squared, y squared, y squared, y squared, y, and that'll add up to 7. So then I end up with 15. X times x times x is x cubed. Y times y times y is y cubed. And then I'm left with 7y on the inside. Now what's really nice is that the same property we just used also works for division. So if we have division, again, we need to have the same index to combine. So if I have 2 separate division problems, like say this, where my index is 3, they could both be 4, they could both be 5, I can write this as one division problem under the radical. So I went from 2 radicals to just 1. I can combine them on the inside. And this is really cool because it helps us simplify. So in this first example, we're missing an x. So you might want to fill that in if you're missing it. We have the square root of 18x to the 5th over the square root of 2x cubed. Since we have the same index of 2, we can combine it as one big radical. Now I'm going to divide. So 18 divided by 2 is 9. And x to the 5th divided by x cubed, remember we subtract our exponents and we get x squared. So now the square root of 9 is 3. The square root of x squared is x. And we are simplified. In this next example, notice we have the same index of 3, so we are good to go to combine. We couldn't combine unless they had the same index. So this becomes 162y to the 5th over 3y squared. In the next step, we're going to divide. So 162 divided by 3 is 54. Y to the 5th divided by y squared, we subtract the exponents to get y cubed. Now I have to simplify, and 54 is not a perfect cube, but 27 is, and 27 goes into it twice. So 27 times 2 times y cubed. Remember, you could also have used your factor tree and found groups of 3. Now, the cube root of 27 is 3. the cube root of y cubed, remember it cancels out, is y, and then we're left with the cube root of 2. In this next one, we're also missing a little x right here. We have the same index. They're both 2 because they're not written. So we'll combine this as 1. So this is 50x to the 6th over 2x to the 4th, which becomes the square root of 25. Now we subtract our exponent 6 minus 4 to get 2, which becomes the square root of 25, which is 5, the square root of x squared, which is x. Now we have one last problem to deal with division. When we're dividing, we cannot have a square root in the denominator. So to simplify a radical expression, we have to rationalize the denominator. So we cannot have a square root in our denominator. So the way that we do that is we multiply the top and bottom by the radical in the denominator. So in this first example, we have 1 over the square root of 2. This might seem simplified, but it's not because there's a square root in the denominator. So we multiply by square root of 2 over square root of 2. Now remember, when we multiply fractions, this is really, we can't actually change the fraction. This is really just like a creative, let's try that again. This is like a creative form of the number 1. We're not actually changing the value of this expression. So we're going to multiply numerators, so 1 times square root of 2 is square root of 2, and we multiply denominators. Now remember, the square root of x times itself is just x. So the square root of 2 times the square root of 2 is just 2 on the bottom. So we're left with the square root of 2 divided by 2. And notice now, there's no radicals in the denominator. In this next example, we have square root of 3 in the denominator, so we have to multiply by a creative form of 1, which is just square root of 3 over square root of 3. And see what we get. 2 times the square root of 3 in the numerator, square root of 3 times square root of 3 in the denominator. Now, we can use our trick for the denominator. Square root of 3 times itself is just 3, so we are left with 2 square root of 3 over 3.